Did you say turn it? No? Let's sit here? Okay. Good. All right. Today we're going to kind of shift topics again. We're going to be talking about kind of two, we're going to start kind of two new areas. We're going to be talking about frequent items and also streaming, and so streaming algorithms. So the idea of frequent items in a nutshell is that we want to find things that occur a lot in some data set, right? And so if they occur a lot, these may be anomalies, these may be some sort of noise we want to filter out. So one of the the key examples that we'll talk about is actually, one of the things that this was, the main technique we'll talk about today was model alignment, was when there's trying to be a denial of service attack on the network. We want to detect this because there's a lot of IP packets going to the same location. So all we'll talk about today will be this frequent items in a fairly abstract sense. And hopefully you can kind of get some idea why these are important for data mining in different contexts. On Wednesday, we'll talk about these frequent sets of items instead, which is a bit more of a complicated problem. There's a bit more modeling involved, and the techniques are slightly different. So we'll talk about that on Wednesday. But just the frequent item stuff, just the frequent items, it's in some sense, if you're just looking at individual items, it should be a pretty simple, straightforward thing. You just keep track of the counts of all the items, and you find the ones which occur the most. So this is interesting. This is more interesting from a computational point of view if your data set is really large. So if the data set is very large, then you can't just keep track of everything in memory. You can't keep a counter of everything that you have to deal with. So what we'll talk about is this streaming framework, which is a way of dealing with very large data. And so I'm going to start by defining the streaming framework, and then we're going to kind of go through some examples of it and come back to the precise definition of the frequent items and see a couple of algorithms for how to do this. All right, so in streaming, the idea is that you have some data set A, and so this data set is not typically, as you might think of it, it's in the memory of your computer, or it's even on the hard drive, but it's coming in some way. So it's there's a stream of things. So think of it like a stream of water, or if you're on a router, there's a stream of packets that are coming through the router. And so if you're sitting here on this router, you see some data come in, and this stream is A, and so this is AI, this is AI plus 1. Each of these are these elements of the stream, and they keep coming into this router, and then you want to process them, and if you're a router, you send them off into one of these other different locations. So the thing, if you look at a router that's sitting on the internet, is dealing with these millions or maybe billions of these packets every day, and the router does not have these huge hard drives on it. Or maybe they can have a pretty big hard drive, but eventually they can't really store everything that comes through. They see it, they do something very quickly, and then they have to send it up. And so what the router does have is some small space of memory. So it's some small memory that it can store some information about it, and you want to keep some sort of statistics on what's going on in this router over the course of the day in the small memory. Now you can't store everything, and you can only see every element once. Once you send it on, if you don't store it in the memory, or you don't do something in the memory, it's gone. Okay, so you're going to have two kind of key properties. You see every element once, and this is in an arbitrary order, right? Maybe if you could pre-sort them, maybe you could do something a little bit more special with it. But you have no control of this. These items are coming through quickly, and you don't control the order. And then the second thing is you have small space. Okay, so you have a very small amount of space, and you see every element once. Okay, so you only see it once, and you have a small space. So it's not like a very typical problem you may cite in computer science, where the goal then is to kind of process some sort of statistic on it in a small amount of kind of trips through a CPU, a small number of comparisons. There you can access things many times over again. Here you can only see it once, and the real constraint is the small space. That's not, it's a C there, small space. So this memory is going to be much smaller. All right, so let's talk about how small is this. So I'm going to kind of talk about, a fairly restricted and abstract model that actually fits pretty well if you're thinking about a router, but this idea can be much more general and have general applications beyond that. And I'll kind of explain some of these after we define this model. But this simple thing is that you say that each element, so each element AI in A, is going to say that this is going to be in some set N. Maybe this is confusing. It's an element of our input data set. So this is the input. And so this is the some sort of domain this is coming over. Right? So we're going to talk about hashing and so forth. So this is going to be something very large. This is going to be something like the so some example. This could be all possible so like all possible IP addresses. So there are huge number of IP addresses. You don't want to store something for each IP address, especially since most of them you'll never see in a router. It could be all possible words. So think like words in a language, or even larger, even all possible keygrams. Right, so you're writing down all possible keygrams. This really explodes in complexity quickly. You don't. There are some. Say if you're looking at like 4 grams for characters, there's some combinations of letters you're probably never going to see, right? Like XKCD, right? You probably never see that in anyone knows the story behind it. So there's some things you probably never see, but you may end up seeing this all the time, right? If someone chooses these 4 letters, like XKCD, then all of a sudden it becomes a very popular set of K-grams. And if you weren't keeping track of it, then if you didn't have some counter assigned for it, then you'd be in trouble. Right? So this set is going to be very large, and so the other quantity that we want to look at is we're going to say that the size of A is going to be equal to some value M. Okay. Now this is only for kind of analysis and thinking about how these algorithms work. in many cases, we don't actually know how big this is going to be, or the stream of data just keeps on coming. It never really stops. But for analysis purposes, we kind of want to look at this value m and say, how big is something, compared to this value m? Right? So if you look at all the packets that a router sees every day, it doesn't want to store every single packet, or even some piece of information for every single packet. Again, this value m is too big. Right? So this could be something like all packets in one day. It could be something like all k-grams in on Twitter. Right. So if you're kind of scanning Twitter information, you don't want to really store the whole Twitter stream. If you do this, it'll probably fill up your hard drive. Depending on how big your hard drive is, maybe in a day or in a few days, depending on what fraction of the stream you're getting. But you don't want to store all of Twitter. You don't want to, if you're keeping track of these k-grams, you don't want to store all of them. You probably just want to keep some sort of, basic statistics on this that you can use for analysis. Okay, so these values m and n are going to be too large. These are going to be much bigger than our storage. So our space, our storage space is going to be roughly something like log of m plus log of n. Okay, and by log, typically you can think of base 2. There can be constants in front of here because it depends on how you model space anyways. And if you change the base, you're just changing that constant. Okay, so maybe we can say something like 100 or maybe 1,000 times this quantity, like log m plus log n, something like that. Okay, so this is exponentially smaller than n and m. Okay, so what does it make sense to? What is this log n kind of? How do you think of this? Right. If this is the space of all IP addresses, that's n. Then what can you store in log n?
The indexes of...
Yeah, you can store the number of possible, but that's not quite as... That's on the right track, yeah?
I meant the indexes of the IP addresses, the same thing.
Yeah, so you can store the label of an IP address, right? So this corresponds with a label, right? So this is like storing one IP address. I said, here's one IP address. Every time I see it, I want to do something with it, right? So if we have kind of a function that says, or I want to say there are two IP addresses, and anything between these two IP addresses, I want to do something about this, right? So that's what you can store in log n, right? So this is all possible IP addresses. So if was like an IP address is how many bits? I should know this by, was it like 16? What? So maybe this is 2 to the 32 or 2 to the 64, depending on what protocol you're talking about. Let's just say it's 2 to the 32. Then log base this is going to be 32 bits, right? So if you're storing one IP address, you need the 32 bits. The log of 2 to the 32 is 32. That's something you can store. You can store one IP address in this space. And so then so what can you think of as log m? What does this log m stands for? Remember, m is the size of the stream. So what can you store in log m?
Just the stream packets, just a few packets.
Yeah, so you could think of it in packets. Packets are kind of a strange thing. So you could think of you could store this is kind of a label, and maybe you can say, an IP address, and maybe there's some meta information. Usually it's not much more than the IP address itself. So that would probably be in the log n. But the log m is kind of a different sort of quantity that we'll also want to keep track of. So if m is, so let's say that, again, if the number of packets we see is going to be like, is going to be, so let's say it's going to be 1 billion. So if it's 1 billion, then that's going to be 10 to the 9, right? Right. So if I take the log of 10 to the 9, so the log of base 2 of this is going to be equal to 9 times log of, what is this, log of 2 over log 10. Where's, I have that flipped. Anyways, this is some sort of constant, right? So this is probably, should be log 10 over log 2. So let's say this quantity is 3. 9 times 3 is like 27, right? So that's 27 bits. So I can store, if I do log base 2, and there are this many things, I can count. So this log m tells me something I can count. I can count how many things I've seen, right? So if I just want to count how many packets I've seen, I need log m space. And so if I want to count anything else, I can do it in log m space. Anything counting roughly the number of things I've seen, I can do in log n space. So you can think of this as a counter. Okay, so basically this log m is a counter, and the log n is going to be a label. So I want to think of some small number of counters and labels of the things I'm seeing, and then what can I do in roughly this space? Okay, so let's say, so let's do a couple of simple questions, and I'll gradually get a little bit trickier. So what if every AI is going to be an integer, like an integer, okay? And so now my goal is the mean, right? So I want to write the mean of A. I want to calculate this in a string. So how would I do this?
Would the current average be take the place of log n for the label, and then the counter be the max or that person?
Yeah, so
So the counter would be the current
so
mean max?
the label is kind of going to use the values, right? And the counter,
Would be the mean, right?
not quite the mean. So the mean I'll write as 1 over m. Right. So I can kind of use the label here and the counter to keep track of m. I need the value m and to keep track of. I can't just keep this value, because what I need to break it into is 2 parts. So one part I'm going to keep track of is the sum, and one part is the total, is the count. Right. So this is a count. This is the sum. This is kind of like a label. This doesn't quite fit this category. I'll come back to this. And so there's actually a slight issue here. The sum of these things may go beyond, like the original log n bits, but it's not going to grow too quickly. You can kind of, create one of these big ints in order to take care of it. So you only need a few of these labels in order to count pretty large. So it's possible to do the mean. You keep 2 things, the total count and the total sum, and then to return it at any point, you divide the total count by the total sum. I mean the total sum by the total count, and you get the mean. Okay. So what if? So this was 1. What if instead I wanted to keep track of the median? right? So now I've got a bunch I've got a bunch of these labels, which are these, say, integers, some large side. I want to keep track of their median. Do you have any ideas? Any guesses? Hmm?
The counter, you can keep track of how many things you've seen so far again, and then as your labels, you can use as the range of values for, like you could have a bit and whether you use a certain index. And then from those indexes, you say for my portion.
Yeah. So it turns out the median is a lot harder. And it turns out you can't calculate the median exactly in space that looks like this. It has to actually be linear in either n or m. But you can't actually do it. You can do it in square root m space in 2 passes. So if you can read over the data twice, you can do it in square root m space. And the more times you can read over the data, you can get smaller space. But for 1 pass over the data, you can't actually compute the median. You can approximate it in a variety of ways, but you can't actually compute it. So certain things, like the median, are actually pretty easy to do. Like the median is very hard to do in a stream. So some things, this small space requirement, and you can only see every element once, makes it very hard to do exactly. Yeah, so this kind of brings up another point I want to touch on. One of the reasons why streaming is interesting is because of the setting, like you're on a router or you're trying to keep track of Twitter, and there's just so much data coming, there's not much you can do. One of the other reasons is even if your data is sitting on disk, and you want to do something, but it's really a lot of data. It's much more than fits in the memory of your machine. Often, doing something that's a streaming algorithm to analyze it will be a really efficient way to do it. When it's on disk, one of the main bottlenecks is bringing it from disk into memory, and you want to minimize the times you do that. And so if you have an algorithm that reads it over the data just once, then it's guaranteed to be basically as fast as possible. It's as fast as just reading the data. Right? So when you have really large data, one thing people often compare to is, you know it's going to take a long time. Well, how did it compare just to read the data? And often streaming algorithms are roughly the same time as just reading the data, and that means you can, as fast as your machine, if your algorithm, streaming algorithm is not fast enough to handle all the data you have, then you probably need a faster machine. There's nothing else you can do. Right? So, but if it's much slower than reading the data, maybe there's something better you can do. Right? So streaming algorithm is in general, this 1 pass over the data is a kind of a fairly useful idea for lots of efficient computation. Well, and if sometimes you can't do it in 1 pass. Like I said, the median, if you only make 1 pass, you need to have space that's either basically linear in n or linear in m. There's no way around it otherwise. But you can reduce that by a square root of the square root of m if you make 2 passes. Now, square roots of m is much bigger than log of m, right? But what is square root of, what's the square root of what's the square root of a billion? Let's say I have a billion items. It's going to be, what's going to be like 10 or 100,000? In the tens of, it's going to be like 30,000, right? So that's, if a billion fits in like, fits in like a few gigabytes, like 10 gigabytes, then the square root of it may fit in a few megabytes. That's actually fairly doable. Even a square root here is actually pretty useful. But it's nicer to think of just these counters in the labels. Okay. Okay. So these were two kind of So these were warm-ups to the warm-up problem. Okay, so now the problem I want to ask is called majority. Okay, so what I'm going to do is I'm going to define some quantities here. So Fj is going to be equal to okay, so this is the number of elements in the stream with value j, right? So j is going to be some quantity in n, right? So this is number of items with value j in n, okay? So this is the frequency of value j. And so we want to find very frequent items. So we have a lot of IP addresses. J would be one of the IP addresses, right? We want to say which IP addresses are very frequent, occur a lot of times. Okay, so now the majority question is if some j has fj greater than m over 2, return j. Else we can do anything. Okay, so it may seem a little strange, but if any counter has more than m over 2 things, so over half, right? So that means that there can only be at most one of these, right? So let's say I'm doing voting, and I want to know if any candidate got over half the votes. If they had exactly half, it was a tie, I don't care, right? If there were 3 candidates and no one got over half, then I still don't care. I can return anything. But definitely, if someone got over half the votes, then I'm, you know, then in that case, I want to definitely return. Okay, so sometimes you have like these write-ins, and maybe your write-in launched a really last-minute campaign, and you want to be able to keep track of these things. Okay, so I want to do this with one counter and one label. How do I solve majority with one counter and one label? So I'm going to have one counter and one label. And we'll call this guy C and this guy L. Okay. Okay. So how do I do this? If you only have one counter and one label, there's really not too many different algorithms you can have. So no, you get one pass. You get one pass with the data. You get 2 passes, it's almost too easy. You can do something much stronger. Let's see. Okay, so let's simulate this on a stream. And I'll just use this stream is just going to be these numbers. So let's say it's 8, 3, 3, 2, 8. Okay. So there are 8 elements in the stream. Let's just say. Okay, there are 9 elements in the stream, and 5 of them are 8, right? So I should have to return 8. Okay, so let's see. I'm going to have a counter, and I'm going to have a label, and so these are the only 2 things I'm going to have available. And so then we'll go through this, and you'll tell me what to do. So the first thing I see is 8. So what should I do? So the label will be 8, and the counter will be will be 1. Okay, I've seen 1, 8. Good, so I've said I've seen 1, 8, I've kept track of it. Now what happens, I see a 3. Well, what should I do? Should we reduce the counter?
Yeah.
Okay, so I have a 0. And what should I do with the label? Keep it at 8?
3.
So at this point, let's look at the string. I have 2 elements. Has any of them occurred more than half the time? No, so I can do anything, right? So how about I just leave it at 8? Sound fine? Okay. Okay, now I see another 3. At this point, I have 3 elements and 2 of them are 3, so I need to return 3. So I'd probably better put 3 in the label somehow, right? And what should I put for the counter? It's got a 1, or a 2?
1.
You did store 3 in here, so how will you know the X and the 3 are in
Well, that's a good point, right? So how do I know? Well, we'll come back and figure out how to write the code for this kind of later. Well, let's kind of go through and see what the counters and labels should be, and then hopefully a pattern will emerge. Maybe? 1? Okay. Okay, so now we see a 2. Well, before we had a label on 1 and we decremented and things worked out. So let's try this again. And I'll keep this 3. Now I see an 8. What? Let's try putting a 1 and an 8. Okay, and now I see another 8. A 2, 8. Okay. I see another 8. I guess I'll increase my counter. See another 8. And so now I see a 7. What should I do? I should decrease the counter. Okay. And I'll keep it as an 8. All right. Good. So now we have to figure out. Now we have to figure out what I did, right? Because as you were saying, how did I know I had to switch the label to a 3 here? How did I know I had to switch it to an 8? Okay, so let's. So basically, when you think of an algorithm, the streaming algorithm is a for loop over all the data, right? So I'm going to have a for, say AI and N, right? So now, the first thing I can do, the first rule that we had is, if AI is equal to my counter, then I'm going to have the label be incremented. Right? This was the step that we applied at least every time we had this 8 in here and we saw another 8. But we did something different at some of these other steps, right? So if it's not the counter, so
You have to
yeah, you're right. Thank you. Okay, so else now if we don't see something that matches, I did it again. All right, I'll just check if you're really paying attention. Okay, I've got it right now, right? Okay, good. Okay, all right. Okay, so now let's say our label does not match the new thing coming in. So what should we do? So we should decrease the counter. Is that always what we did? Well,
Not
at this point,
Or switch it if, when the counter is 0, then we switch to the label.
yeah.
As we pick the counter.
Okay, so let's try something else. Let's say, have a special case if the counter is equal to 0. Right? So let's say initially, before I saw anything, the counter was equal to 0. Now, if the counter is equal to 0, this means I get to choose a new label, right? I'm going to set the label equals to AI, and I'm going to set the counter equal to 1. Okay, so that's what happened. In the first step, the counter was 0. I get to set a new label, and I get to set the counter equal to 1. I also had it here. When I saw this element, the counter was 0, so I can swap the label to 3, and I can increment it to 1. And it also happened here. The counter was 0, so I can swap it to 8. Swap the label to 8 and increment by 1. This is the only place where I ever swapped the label. Right? Initially here, and then at these points. And this always happened because the previous counter was 0. Okay, so now there's one last case. If this is, so, like these. So else, so that means the counter is not equal to 0. So then I just set, so then I'm just going to decrement this counter. All right, so this is the whole algorithm. It's a very simple algorithm, right? So does this match, does this algorithm match what we did? You don't think it's correct?
So 8, 8, 3, 3, 2.
8, 8, 3, 2. Is there anything that was majority in that?
Oh, 8 and 3 still doesn't matter.
Yeah, there's 8 had 2/5, 3 was 2/5, 2 was 1/5. So they're all under majority.
Yes.
Yep.
So what if you had like 8, 8, 5, 4, 3, 2, 1?
Was anything a majority?
8, 8. Is that how we're defining the majority?
Okay, so let's see what 5, 4, 3, 2, 1. Okay, so there was a point where 8 is a majority. The first,
Oh, so you're saying,
at
okay.
every point in the stream, this should be true. If I stopped here, it should be true.
I think I'm misunderstanding majority, that's why.
Yeah, so it's a very precise definition here. If the frequency count is greater than m/2, I have to return j. If there's nothing that satisfies this, and there can be almost one that does, I can return 8. So at some point in the stream, I did have